In this lesson, we're going to introduce an algorithm for curve sketching. So it's just basically a series of steps that you follow to help best sketch a curve. Okay, so I'm not going to go through each of the steps. They're listed right here on the page, and you can read them on your own. But I will refer to them as I go through the next example. So it says here, sketch a graph of y is equal to x plus 1 over x squared. Well, the first thing that I'm asked to do in my algorithm is to look for any vertical asymptotes. So these are values of x that are restricted. And I can see that there is a vertical asymptote at x is equal to 0 because that would cause the denominator to equal to 0 here. But because the degree on the x value is even, that means that it's going to approach the same extremes. Okay, so that means it's either going to approach positive infinity on either side of the asymptote, or it's going to approach negative infinity on either side of the asymptote when you have an even degree asymptote. Okay, so the next thing on the algorithm is to find the x-intercepts. So to find the x-intercepts, what I need to do is I need to set y equal to 0. So to set y equal to 0, I do this right here, and then I get x plus 1 over x squared. Well, all of this right here is a rational equation, and because it's an equation, I can multiply both sides by x squared, and then I'll have 0 is equal to x cubed plus 1, which can then be factored into x plus 1 and x squared minus x plus 1 using the difference, or rather the sum of cubes formula. I know that x is equal to negative 1 so that's 1 x-intercept. But if I try to find the roots of this right here, we can just check using the discriminant of the quadratic formula. So b squared minus 4ac. If I find b squared minus 4ac, so that means negative 1 squared minus 4 times 1 times 1. I get negative 3, so that means I have non-real roots. So there are no zeros caused by this trinomial right here, so the only x-intercept, this right here, is the only x-intercept right here. This is the only x-intercept. The next thing that we have to do is we have to look at the end behavior of the function. So the limit as x approaches negative infinity of this function. Well, if I see as x approaches negative infinity, okay, you don't have to include this note right here because I'm going to erase it, but as x goes to negative infinity, this value goes to negative infinity, and this value goes to negative infinity squared, but since it's in the denominator, 1 over x squared is going to go towards 0. So this term is going to go towards 0 because x is in the denominator, and when the denominator gets really, really big, the whole number goes towards 0. So what I'm going to write here is that the limit as f of x as x goes towards negative infinity is equal to right here, that's equal to negative infinity. Same thing, the limit as x goes to infinity, positive infinity. Well, this first term goes to positive infinity, and this second term goes to 0. So positive infinity. Now, this is a rational function, so I need to check if there are any oblique asymptotes or horizontal asymptotes. Okay, so what I'll do right here is I'll change the way this looks by taking this x value right here, multiplying it by x squared over x squared, so I'm giving it a common denominator with the second term. Okay, and then I get y is equal to x cubed plus 1 all over x squared. And I can see that the denominator is 1 less of a degree than the numerator, so I'm going to perform some long division here. And so I go x cubed plus 0x squared plus 0x plus 1. Okay, x squared goes into x cubed x times, and then I get x cubed, and I subtract those. I get 0, and I bring the 1 down, plus 1. That's my remainder. So because I have a remainder, what I end up with is I end up with an oblique asymptote. Y is equal to x is an oblique asymptote. Okay, so I have a vertical asymptote, I've got the x-intercepts, and I have the end behavior of the function. Now what's required of me is to look at my first derivative. Okay, so now what I'm going to do is I'm going to look at y prime. Okay, and y prime, so we're going to look at first derivative. We're going to see where the function is increasing, decreasing, maxes and mins, that sort of thing. Okay, so when I find y prime is going to be equal to 1 minus 2 x to the power of negative 3, or y prime is equal to 1 minus 2 over x cubed. Now you might be thinking, oh, well, is 0 a critical number because it makes the first derivative undefined? Well, no, we had a restriction for x is equal to 0, so 0 is not a critical number. However, we can make this equal to 0, and we can say 1 minus 2 over x cubed, and then bring everything over and rearrange. So 2 over x cubed is equal to 1, and so x cubed is equal to 2, and then x is just the cube root of 2. Okay, so this value of x makes the first derivative equal to 0. So that means it could be a max, it could be a min, or it could be a flat POI. All right, so what I'll do right here is I will create a table. So for x less than 0, so even for the values that where it's undefined, I'm still going to include that in my table, my sign table for the first derivative, between 0 and the cube root of 2, and then for x greater than the cube root of 2. All right, and I'm going to look at my first derivative and see what its values are. Well, when x is less than 0, my first derivative is positive. When x is between 0 and the cube root of 2, my first derivative is negative. And when x is greater than the cube root of 2, my first derivative is positive. Okay, so what do I know right here? What does this tell me? Well, this tells me that the function changes from increasing to decreasing across the vertical asymptote of x is equal to 0. Now, remember that the cube root of 2 made the first derivative equal to 0, so that means it's a max, a min, or a flat POI. And there's a sign change. The function's decreasing to increasing. So that means that this right here is a minimum. So at x is equal to cube root of 2, there is a minimum. And so I plug the cube root of 2 back into the original function to find what its y value is. And I get approximately, okay, so this is approximately 1.251.89, okay, is a minimum. And so I'm just going to clean up that approximately sign. Okay, that's where my minimum is located. All right, the next thing that I'm going to do is I'm going to see if I have enough information to determine, to see if there's any use in going on and doing the second derivative. Okay, so I'm going to plot some of the things down here that I know. Okay, so I know that I have a vertical asymptote at x is equal to 0, so I'm just going to freehand this. Okay, so at x is equal to 0, I've got a vertical asymptote. That was a restricted value in the domain. I also had a oblique asymptote at y is equal to x, so I'll put that over here. This is y is equal to x. There's my oblique asymptote, okay? I know that I have a minimum value at 1.25189. So 1.25189, there's going to be a minimum value right here, okay? I also know that I have an x-intercept at -1 and 0. Okay, so if this is a minimum value, and then I can also look at right here, I say that my function is decreasing after the VA, but increasing before the VA. So decreasing after the VA, that makes sense. It goes down to the minimum right here, and then goes up this way, okay? And then over here, and remember it's going to approach the same extreme because it was an even degree asymptote. So now over here, my function will be increasing. Okay. All right, and I know I don't have any changes in concavity because I was given only one minimum right here, and that was this right here. So it's concave up on this region of the function, okay? And it just goes to a minimum here. Okay, so that's enough information for my my graph of y is equal to x plus 1 over x squared. You'll see, though, that we stopped at doing the first derivative. Often you'll have to go and do the second derivative to find points of inflection. So let's go and take a look at the next example right here. And the next example says, sketch a graph of this right here, x to the power of 2 over 3, bracket 5 minus x. We see that this is going to be a continuous function. So the first thing that I had to do is I had to find my VAs, and there's going to be no vertical asymptotes. It's a continuous function. There's no value of x that is restricted here, okay? And then I'm going to have to find my x-intercepts. So I'm going to set this equal to 0 and look at the values of x that make this equal to 0. Well, we can see that x is equal to 0 is a possibility, and x is equal to 5 is a possibility. So 0, 0, and 5, 0 are my x-intercepts. Now, what I'm going to do here is I'm going to look at my end behavior. Okay. And remember, for your end behavior, you're looking at the limit of the function as x goes towards negative infinity. Okay, so let's take a look at this. As x goes towards negative infinity, what happens to this right here? X to the 2 over 3 would go towards, as x goes towards negative infinity, well, because it's squared, it's going to become positive infinity. So x is going to go towards positive infinity. Now let's look at this factor, 5 minus x. Well, as x goes towards negative infinity, this is also going to go towards positive infinity. So I can therefore say that the limit as x goes towards negative infinity, the limit is positive infinity. This factor times this factor right here gave me positive infinity. Okay, let's look at the next one, the limit as x goes towards positive infinity of f of x. Okay, and so we'll look at the different factors. X to the 2 over 3 is going to go towards positive infinity, but 5 minus x is going to go towards negative infinity. So a positive number times a negative number is going to make a negative number. So if I look at this, it's going towards positive infinity as x goes towards negative infinity, and it goes towards negative infinity when x is positive infinity. So that means that I'm going from quad 2 to quad 4. Okay, so I've got my VAs, they're none, x-intercepts, 0 and 5, and my end behaviors. All right, now what I'll do is I'll look at the first derivative. And so for the first derivative, I'll take this function right here, x to the 2 over 3, 5 minus x, and I'm going to expand in and use my power rule, so 5x to the 2 over 3, and then over here this is going to be minus x to the 5 over 3, because if I take x to the 2 over 3 times x, that's the same thing as saying x to the 3 over 3, and I add the exponents. This form is way easier to find the first derivative, so keep it in this form because now we just use power rules, right? Okay. So then 10 over 3 x to the negative 1 over 3 minus 5 over 3 x to the 2 over 3. And ideally what you should do is you should look for the smallest numbers that they have in common. So in that case right there, x to the negative 1 over 3 is the smallest of the two terms that they have in common, and 5 over 3 is the smallest. So we're going to factor those out. So if we factor 5 over 3 and x to the negative 1 over 3 out, what we should end up with is, in these brackets here, 2 minus x. All right, so this will allow me to do a analysis of the critical numbers. So x to the negative 1 over 3 would put x in the denominator. So x is equal to 0 is a critical number, and it's undefined. So if it's undefined, that makes it possibly a cusp or VDT. The other possibility is x is equal to 2. That makes it 0. It makes the first derivative equal to 0, so that could be a max min or POI. What I'll do here is I'll do a sign table, and so I'll do the various factors over here. So 5 over 3, x to the negative 1 over 3, and then 2 minus x, and then my overall first derivative. Then I'll have x less than 0, between 0 and 2, and then x greater than 2. And I put in the signs for the various factors. So you can work these out. If x is less than 0, then this would be negative. Between 0 and 2, that makes this positive. And x greater than 2, yeah, that would be positive. If x is less than 0, well then this right here is going to be positive. Between 0 and 2, this still stays positive, but if x is greater than 2, then this becomes negative. So overall, this is negative, this is positive, and this is negative. Well, we know that when x is equal to 0, it was undefined, so that made it either a cusp or a VT. Since there's a change of sign, it is a cusp, right? There's a change of sign, so there is a cusp at 0, 0. And then at 2, we have it going from increasing to decreasing, so therefore we have a max at 2, and then again, I'm going to take that 2 value right there, plug it back into this original equation, okay, and find an approximate value. So 2 and approximately 4.8, okay? So what I'll do is I'll take that out right there, and I'll put this right here. So approximately 2 and 4.8, okay? So I've got a cusp, and I've got a max. Great. Now what I can do is I can look at my second derivative, right? So this was my first derivative right here. Now I can look at my second derivative. So if I have my first derivative, I'm going to put it back in this form right here. 10 over 3x to the negative 1 over 3 minus 5 over 3x to the power of 2 over 3. And what I'll do right here is I will find the derivative of this using this form. Okay, so let me just get rid of this right here. Okay, so y double prime is equal to negative 10 over 9x to the negative 4 over 3 minus 10 over 9x to the negative 1 over 3. Well, I see this right here and this right here being my lowest factors in those two terms, so I can factor those out. And I get negative 10 over 9x to the negative 4 over 3, and then 1 plus x. Okay, so what makes this equal to 0 is when we have x is equal to negative 1. So x is equal to negative 1 makes that 0. Also, 0 makes this undefined, so that means I'll use that as my intervals for my sign table of the second derivative. And then I take each of the different factors, 10 over 9, x to the negative 4 over 3, and then 1 plus x, and then overall my second derivative. Well, if we sub in a number less than negative 1 over here, this one right here is going to be negative, negative, negative. And that's because any number right here is going to be raised to the power of 4, so this makes any number positive, but then right here we have a negative coefficient, so it's always going to be negative. This 1 plus x will be negative here, but positive here and positive here. That makes my first, or rather my second derivative here positive on this location, negative here, and negative here. So remember that negative 1 caused the second derivative to make it equal to 0. Negative 1 makes the second derivative equal to 0. And we have a sign change, so that means that negative 1, and then plugging negative 1 back to my original function, negative 1, 6 is a POI. And that's because negative 1 makes the second derivative equal to 0 and causes a sign change across that table. Okay, surely I have enough right now. So let's start with my x-intercepts, 0 and 5. Okay, so let's put these in right here, 0 and 5. Okay, I have a maximum at 2 and 4.8. So 2 and 4.8 right there. I've got a cusp at 0, 0. Okay, and I've got a point of inflection at negative 1 and 6. So at negative 1 and 6, okay, I also know that before negative 1, it's concave up. And then it's concave down for the rest of the function. Okay. So I'm going to go concave up right here, concave up, and then I'm going to create a point of inflection, and now it's going concave down. Remember, 0, 0 is a cusp, so it's going to bounce back to a maximum and then proceed down. Like this. Okay, so I've got my maximum, I've got my x-intercepts, I have concave up to concave down, and then concave down for the remainder of the function. Okay? Put an arrow here. The last thing I want to check, am I indeed going from quad 2 to quad 4? Yes, I am, quad 2 to quad 4. So this is roughly the shape of my function. Okay, obviously yours will look a lot smoother, but because I'm just using a digital tablet here, it's not as accurate, but yours I'm sure will look way better when you present it. Okay. Yeah, essentially it's just a matter of looking through the different steps of the algorithm. You start by doing your vertical asymptote, your x-intercepts, your end behavior, then you do the first derivative and look for increasing and decreasing regions, critical points, second derivative, and you can find points of inflection. Okay? All right, thanks for watching, and there's a list of possible questions you can do on the next page.